Okay, so this lecture is about some uh, initial concepts, some introductory concepts related to signal design and signal timing. And we will go through some of the basic concepts, some basic terminologies, the components of the signal system, and some other things. And this is taken from chapter 5.5 of the book which we are following, which is this book. The name of the book is Highway Engineering, Planning, Design, and Operations. And it is written by these gentlemen. So let us begin. So traffic signals are the most analyzed form of intersection control because of the obvious reasons that we are basically deciding everything is not left to the driver's judgment like it happens on roundabouts and stop signs. So, but it may not be the common one, the most common one, especially in areas where the population is low, the suburban neighborhoods, low density areas, the traffic signals do not provide the optimum solution for intersections there because of low traffic conditions. Okay, but in spite of this, like I mentioned earlier, this most analyzed form of intersection. Okay, and it becomes more important on corridors which have congestion problems or which have high traffic demand. Okay, so obviously these are important roads, and on these important roads you will very often find traffic signals being used. The components of the traffic system can be divided into two parts or two types: hardware components and software components. Hardware components can be further divided into two subtypes or subparts. One is signal control cabinet. So there's a cabinet at the side of the signal. You will see it very close to the intersection, especially in Bahrain. I don't know, I'm not much familiar about the other locations, but even in Pakistan, you will see these cabinets. Uh, they are sometimes can be directly attached to a signal just on the ground level, or they can be close to the intersection in the same vicinity. And then we have sensors, detectors, which are attached to the signal, and these sensors and detectors can be used for collecting traffic data and managing signal on that basis. And these sensors and detectors can be on the roadway, inside or under the roadway, or they can be on the side of the roads. Then we have the software components. So there's a local computer within the controller. Okay, so in the controller cabinet, there is a computer which is controlling that particular signal. And then we have an interaction platform between the computer and the traffic management center, which is now very common that there's a traffic management center which can manage the traffic signals from their office. The hardware components, now we are going in more detail. We have a signal controller. So most of them, as you would see, that most of them are in the controller cabinet, which I mentioned earlier. So we have a signal controller, which is the computer containing the logic to run the intersection housed inside the cabinet. So this computer is housed inside the cabinet, which we are calling a signal controller, and this is containing the logic how the signal will run. Okay, like what timings, what will be the sequence of timings to be uh, to say it in a very crude form, the sequence of signal timings. Okay, uh, and for different directions. Then we have the mail function unit or the conflict monitor. So this conflict monitor is basically applying some rules on the logic which you have provided with the computer. So this logic is checked under some rules, and whenever there is a rule violation, then the mail function unit or the conflict monitor will detect it. Okay, and it will turn the signal, or it will not let the signal run normally. So it will start flashing, the signal will start flashing. So since it is not performing the normal operation, so the drivers would know that we are on our own in this case. So what can be the rules which are applied to this which are applied by this malfunction management unit. For example, the programmer, like myself, may make a mistake and allow two conflicting movements having the green time at the same moment. So obviously it will create a conflict that you are allowing two conflicting movements to enter the intersection at the same time. So the programmer made the mistake, but the malfunction unit will detect that mistake and make sure the signal goes into a flashing mode. Okay, so no movements are happening according to the signal in that case. So the the people would know that there's a problem and they will try to rectify it. Then we have a detector rack, which is a space in the cabinet. It has, this rack has different cards. Okay, we call them detector cards. And these are the hardware components that receive the call from the in-road or above ground detector sensors and translate them as input to the signal controller. So obviously we are talking about an intersection where the signal is installed. So if you are going with the detector could be installed in different directions. So each detector could be connected to a different detector card. And when the signal comes from that sensor to the card will translate it into some sort of an input, like in terms of number of vehicles or the speed of the vehicles, and then it will be sent to the signal. Then we have the field terminal, which is the interface between the internal and external wiring at the controller. Okay, so the internal wiring is within the cabinet, and the external wiring is going from the cabinet to the signal, and the interface between them is called as a field terminal. Then we have field transfer relays, load switches, and flashers. These are the hardware components which have the software and the hardware components to interact with each other, to communicate with each other. Okay, so the softwares are running the logic, but that logic activates the hardware through these relays, switches, and flashers. So for example, relays physically transmit a pulse signal to a hardware device. Okay, the load switches control the uh, change of the different signal indications. So it goes from red to yellow to green. Okay, so these load switches are being pushed around. Okay, not pushed around like they are changing. Okay, and these load switches are causing the lights to change. So they are taking the signal from the relay and then they are activated and changing the lights. And flashers control the on-off sequences for beacons, or when signals are in flashing mode. So whenever there's a malfunction or manually the signal is operated in the flashing mode, then these flashers take control. Then we have police switches. These are installed so that signal can be controlled manually if it is required. In Bahrain, it's a very common phenomena in congested conditions that you will see a policeman with the signal cabinet, and he is playing around with the signal, not playing around, but in the true sense of the word, but like he is controlling the signal and he is allowing the movements and so on. So you know some people get angry at them, but that poor guy is just trying to do his job in very tough conditions. Okay, the information flow for a signal. So signal sensors and detectors, they we have moving cars coming towards the intersection. Then we have inductive loops or detectors which are taking the data of these moving cars. Then it is transmitted to the detector amps or the detector cards. Then these detector cards transmit the data to the controller, which sets up the logic according to the data. Then the signal lights are controlled through relays and switches, and they change according to the data. And then according to the lights which are being shown, certain movement of traffic gets the right of way, and when they get the right of way, we have the moving flow, and again the cycle continues. So signal timing process, the process to calculate signal timing follows 12 steps. The first step is to identify the left turning movements for all intersection legs, okay, and their treatment. Okay, so how many left turning movements you have, what type of treatment do you want for them. Then we have to identify the lane groups. you have to determine the traffic data for each lane group, and this data will include finding out saturation flow rate for each lane group, volume, and then finally do the volume to saturation flow rate ratio. Then we develop the desired phasing plan for the intersection, calculate the yellow and all red times, find out loss time for each phase, and add the loss time of all phases to find out for the cycle. Uh, Select a target volume to capacity ratio. This is like a design input. Estimate the cycle length for the intersection. Calculate effective green time available per cycle. Okay, distribute effective green time across the phases. Calculate the actual green time and check pedestrian clearance times. We have already discussed some of these terms earlier. Just to refresh your mind, loss time is the time during which no movement is supposed to enter the intersection. Effective green time is the phase time minus the loss time, and actual green time is the time when you see the green light. Okay, and pedestrian clearance time comes from the pedestrian requirements. Okay, so we said that first step is to find out the treatment of the left turn. Left turn treatment can be protected or permissive. Protected means that the left turning is bound by the signal, or you can say it is protected by the signal. So when you're designing the signal, you are giving it a separate phase, and the vehicles are supposed to wait for that phase, and obviously when that phase comes, the conflicting movements are being stopped. That's why it is called as protected. Permissive is they will just take the left turn whenever they feel safe. So there is no phase for them, but they can take the left turn when they feel that they have enough gap in the opposing traffic to take the left turn, and you can apply a combination of them. Just one thing to be kept in mind, which is when we say the opposing movement, we will use it again as well. So whenever we say the opposing movement basically means if I'm taking this left turn, then opposing movement is this guy. Okay, so for this left turn, this is opposing movement. Okay, opposing movement doesn't mean the left turn from the opposite side. It is a straight from the opposite side which will conflict with the left turn. Okay, so how do I decide whether the left turn should be permissive or protected? They have given us a third category as well, which is a combination of permissive and protected. So sometimes in some traffic conditions, one intersection will have a permissive left turn movement, some other condition it will have protected left turn movements. But I would say that it will create confusion for the drivers, that he doesn't know what to expect when he is coming to the signal. And obviously in that case you have to give him extra caution and extra warning and extra information about what is the condition right now at the signal. Okay, so how do I decide whether left turning should be permissive or protected? It is according to these conditions. Okay, so like I already mentioned, opposing means this one. Okay, so if you multiply the left turning movement volume with this movement volume, okay, so this one multiplied by this volume, okay, volume. So if the answer comes out to be more than 50,000, and you have one lane here, the opposing movement is one lane, then we would say make the left turning movement protected. Okay, so if there is one opposing lane, the product of opposing volume and the left turning volume, if it exceeds 50,000, we'll make the left turning protected. For two opposing movement, it should exceed 90,000. For three opposing lanes, it should exceed 110,000. So in all these cases, the left turning should be protected. When you exceed these limits, the left turning should be protected. Other reasons for which you make the left turning as protected, one could be sight distance. So you saw that for left turning guys, there's not enough sight distance, so they can judge the gap properly from the opposing traffic. Then you have to make it protected. The opposing vehicle is coming at very high speed, very high meaning 45 miles per hour or more. In that case, we, to avoid the severity of the crashes or very severe crashes, we will prefer left turning to be protected. If you have presence of more than one left turning lane, so the number of left turning lanes, designated left turning lanes, okay, are more than one, then in that case it can become confusing for the drivers, okay, and they may conflict with each other in order to find a gap. So this driver is going in this direction, there somebody is going from the other lane as well, okay, and there can be some confusion between them, and they may be trying to avoid car from here, they may crash with each other. So it is easier to make them to make it protected to avoid this confusion. And the last thing is the experience of crashes. Okay, so the numbers are fine, the speed is low, side distance no problem, you don't exceed the limits, but the crashes are happening on the left turning. So then you don't have any choice. Okay, so uh, you know, in that case you will go for a left turning protected phase no matter what, because it's shown. Okay, then you identify the movement groups and the lane groups. Just to restate what we said earlier about movement groups. Movement groups consist of those lanes which have a common movement. Okay, so you can see there. So for example, this is one movement group, another movement group. So you can see the common movement in them. Okay, and this is the third one. Okay, so the movement group will be these. The 2x, the left turning will be one movement group, and these three will be another movement group. Okay, because there's a common movement in these three, and there's a common movement in these two. Okay, and lane groups are the lanes which have the same capacity, and the capacity depends upon and the type of movements. So the lane group consists of all lanes which have the same movement. So this is one lane group, there's another one, another one, another one. Okay, so whenever any movement is changing, we are putting in the other group. So these two lanes have the same movement, these two lanes have the same movement. This one has a right turning added, so it's in the third lane group, you can see it here. Then you determine the lane group traffic data for each lane group, find out its volume in each lane, find out the saturation flow rate for each lane, and then you divide. Saturation flow rate for one lane group would be same per lane because all the lanes have the same configuration. Okay, so saturation flow rate, if you have 3 lanes in one lane group, all 3 lanes will have the same saturation flow rate. And then you calculate the V by S ratio, the volume to saturation flow rate ratio for each lane group. Okay, then you will find out the phasing plan. In finding out the phasing plan, the points which we have to keep in mind, that the addition of V by S ratio from the lane groups of each phase should not exceed 0.8 to 0.9. Okay, if it goes more than 0.9, then you are going in a very dangerous zone, and the signal may not work properly during the peak hour. Okay, so we try to keep the summation of V by S ratios for lane groups in different phases. Okay, let us look at some of the notations which they use in determining the phasing plan. This is what we call the phasing plan. Okay, so you can see movements from different directions are shown in different boxes. If they are happening at the same time, we make the boxes parallel to each other. So these left turnings are happening parallel, these are happening parallel, these are happening parallel, but since they are in different directions, so you see them in different boxes. Okay, so each direction is called as a different ring. Okay, so this is one ring, this is another ring, and so on and so forth. The numbering of the movements also follows a pattern according to this book. You can devise your own pattern, no problem. So the straight movements are uh, you know are numbered with even numbers. Okay, the left turning has odd numbers. Okay, and the right turning is the the number given to the straight movement plus plus 10. So if the straight is 6, then the right turning is 16. Straight is 4, the right turning is 14. Okay, and in deciding these numbers, we start from the major movement and go towards the minor. So major movement is very easy, the movement which has higher volume, or the movement which has higher V by S ratio, that becomes a major movement. So you start numbering from that movement. Okay, and the rest of the numbers, like if you already numbered, so if it is a straight movement, you will give it an even number. Okay, and the right turning of that one will have plus 10 its number, and the left turning will have an odd number. Okay, so you start from 1, but if it's a straight movement, instead of 1 you will put 2 if the major movement is there, and then its right turning will be plus 10. So if it is 2, then the right turning will be 12, and so on and so forth. For pedestrian movement, we code it with letter P. Okay, and the number comes from the straight movement which is happening in the same direction. So you can see this is 8P, because there's the straight movement which is 8. So we add P to show that this is not the number 8 doesn't show the vehicle movement, it is showing the pedestrian movement. Okay, so 8P, and this one is 2P because there's a movement 2 here. This one is 4P because there's a movement 4 here, and so on and so forth. Okay, and yeah, I think I covered everything. Then you calculate the yellow and the all red times. Okay, so yellow time is also called as the clearance time, and all red time is called as the change interval. So yellow time is given for the drivers to think and decide whether they want to go on or stop. Okay, whether they want to whether they feel that they will cross the signal during the yellow time. Okay, so we cannot make green to red directly, because green means go and red means stop. Okay, so you make the signal suddenly go red, the driver has to brake very hard, and then there will be crashes. So we give this yellow time, so driver will decide. Driver knows the signal is about to become green, about to become red, and he will decide what he wants to do depending upon his speed and his position. Okay, so the distance in which the driver is deciding this, we call it the dilemma zone. Okay, so dilemma zone is a zone in which the driver has both options. Okay, he is not so far from the signal that his decision will always be to stop, and he is not so close to the signal that his decision is always to move. Okay, so I'm just 2 feet away from the stop line, the signal becomes yellow, I don't have to think, I will just go. If I'm 30 meters away from the signal and the signal becomes yellow, there's nothing to think about now, I have to stop. Okay, a dilemma zone is something between them, and you can see it over here. Okay, so if I'm here, I'm too close, I'll go always. If I'm here, I'm too far, so I'll stop always. But there is a overlapping between them, and this is what we call as the dilemma zone. So normally they put some sensors here. Okay, we call them the loop detectors. So loop detectors sense the signal, sense the vehicles which are here, and if these vehicles are, if they're the vehicle in this zone and that vehicle has a certain speed, the signal will extend its yellow time, so to help this driver go through it. Okay, so otherwise this driver may cause a rear end collision because of his indecision. So in order to help this driver make the decision, we put a sensor. So if this driver is confused, at least the driver has more time, more yellow time to pass. Okay, that's the critical thing. All red time is given just before the signal turns green. Okay, just before the signal turns green. In Bahrain it turns yellow, so we can say, yeah, it turns yellow before green. So you can say that when the signal goes from red to yellow, okay, so at the end of red there's a small portion of all red. So the other signal went from yellow to red, and the next signal is supposed to go from red to yellow. So there's a small gap in which the signal has already become red, the previous one, and the next one is still red. Okay, it's 1 or 2 seconds. Again, is for the drivers who are already in the intersection. Okay, so don't take it from me and say that yeah, signal, the next signal is not supposed to become red, so I should enter the intersection. That is all. You do it at your own risk. Don't blame me if you get hit by some other car. So the all red time is very short interval, just for the sake of the drivers who are already in the intersection. You just want to make sure that they cross, okay, or they clear the intersection before the next signal becomes green. So that's why we call it the clearance interval. Okay, all red is also known as the clearance interval. So this is the next step. So clearance interval can be calculated using this equation, and this equation, there are two parts. This part will help you calculate the yellow time, and this part will help you calculate the all red time. Okay, and the addition of these two is known as a clearance interval, addition of yellow and all red. Okay, so so TPR plus this will give you the yellow time, and this one will give you the all red time, and this equation comes from the equation of stopping side distance. Okay, so we took the equation of stopping side distance and we rearranged it to give us the time instead of the distance. Okay, and this is the equation for all red time. Now what is S naught here? S naught is the speed of the vehicle, normally taken as the 85th percentile. A is the deceleration rate, capital G is the gradient, small g is the gravitational force, TPI is the perception reaction time, W is the width of the intersection and the direction of travel. Okay, so intersection is like this box, right? So if the driver is coming from here, then this is W. Okay, this is W. So we need the width in this. So it's from a stop line to the other direction. This is W. And L is the length of a standard vehicle, which is taken normally as 20 feet. Then you find out the lost time per phase, and you find out the lost time per cycle. Now each phase has two lost times. One is all red. And the other one is one is all red plus some portion of the yellow time. Okay, we call it the clearance lost time. Okay, so what happens normally, we believe the drivers are more cautious. Okay, so the driver who was very far, let me go here. So there's, let's say, some driver here. So he was coming and he saw the signal is yellow. So he came to the intersection, but since he was far, he already decided I want to stop. Okay, and but his his judgment was on the safer side. This is what we are assuming, that his judgment was on the safer side. So even when he reached the intersection, signal was still yellow. Okay, now I think it happens the other way around. People who even are too far, they decide we want to go. So when they reach the signal, it's actually red. But anyway, this is how the procedure goes. You are assuming the driver will decide on the safer side. So even when the yellow time is still remaining, but it is just the end of yellow time, so those drivers who are even reaching the signal at the end of yellow time, they will also decide to stop. So this is why the clearance lost time includes all red, because we call it the clearance time, and some part of yellow as well. Okay, so they are saying the clearance lost time is 1 or 2 seconds. So all red plus the last part of yellow is 1 or 2 seconds according to them. But in Bahrain, even the all red time is, I think 2 or 3 seconds. Okay, it goes to show the aggressive nature of the drivers. Okay, so you need to find out, okay, what part of yellow time is used. Maybe none. Okay, and then we have the startup lost time. Startup lost time is the extra headway which is taken by the first 3 or 4 vehicles in the queue to pass the intersection. The first 3 or 4 vehicles, when they cross the stop line, they are going slower, so their gap, the headway between them is larger than normal, because of the speed and because of the time they have taken to get the vehicle moving. They have to put the phone somewhere, maybe have to put the car in gear or whatever. Okay, so these cars, their headway is more than normal. Okay, so this more than normal headway is what is our startup loss time. Okay, so the normal headway starts to be observed after the fourth vehicle from the queue. Okay, so you observe the first 3 4 vehicles, they will give you a certain value of headway, each one of them, and then you observe the other vehicles of the queue, the one who came after the fourth vehicle, and then their average, the one who came after the fourth vehicle, their average headway is considered as a normal, because those guys were coming at higher speed, they had more time to prepare, and so on and so forth. So if you take the difference of that average value which you observed after the fourth vehicle and the value which you had for the first 4 vehicles, you take the difference between the average and the value of the first 4. This difference is called as the startup loss time. And they have again given us a recommended value which is 2 seconds. You can see the how the headway uh, depletes from the first vehicle to the fourth vehicle. For the first vehicle, the headway is very high, first 2 vehicles, then it starts to go down and then it almost reaches a constant value. Okay, if you have overlapping phases, so there are phases in which the movements are continuing from one phase to the other, we call them overlapping phases. So in case of overlapping phases, you will just use a loss time of one phase for a movement. You will not say, because the movement is continuing, it didn't stop. Okay, so the loss time for that movement only happened once. Okay, when it stops or when it starts to go down or when it starts to when it starts again. Okay, so it depends upon the movement, not how many phases are being changed. If the movement is not stopping, it will not encounter the loss time, the clearance loss time. If it is not starting again, then it will not have the startup loss time. Okay, so startup loss time happens when the movement starts. Clearance loss time happens when the movement has just ended. Okay, so it depends upon when the movement has started and ended. Okay, so you can take these values of loss time for each phase, so they will be between 3 to 4 seconds. Okay, or you can get your own value, do the observations and you get your own values. A phase time includes green plus yellow plus all red. Green plus yellow plus all red. Effective green includes the phase time minus the loss time. Effective green, phase time minus the loss time. Okay, so for each phase we will have an actual green, a yellow and all red. I already showed you the equation for yellow and all red. For the green time, we will discuss it later on. So you will calculate the effective green, which is the phase time, the full phase time minus the loss time. And then if you have 3 phases, add the loss time of all these 3 phases, you get the total loss time of the cycle. Okay, because cycle is a combination of phases. Okay, then the design value for volume capacity ratio. Okay, so at what value you want the volume to be in terms of capacity in the peak hour, or how much extra capacity you want in the peak hour in relation to the volume. So if I need the capacity to be 10% higher than the volume, then the volume capacity ratio will be fixed at 0.9. Okay, so 90% of the volume is capacity. Capacity is equal to volume is equal to 90% of the capacity, and then you have 10% extra for a margin of safety or for some unexpected situation. So normally we take between 0.85 and 0.9. If you are using actuated signals, so in actuated signals we can make it higher, even go up to 0.95, because actuated signals are run on real-time traffic. So we don't need so much margin of safety because it's real time. Okay. For calculation of cycle length, we have 2 equations. You can see them here. One is Webster's equation. The other one is, I don't know, there's no name for it. I call it the regular traditional equation. Okay, what are we using here? Capital C is the capacity, XC is the volume capacity ratio, the design value which you have selected, and I told you it can go between 0.8 to 0.9 and maybe up to 0.95 for actuated signals. This is XC, and V by S ratio, volume to saturation flow rate ratio. Okay, so capital C is the capacity of the signal, which is with the signal timing. And saturation flow rate is an imaginary value, a theoretical value, a hypothetical value. So it does not have the consideration of the lost time. Okay, so this is the difference between capacity and saturation flow rate. And the other difference here is in this equation, saturation flow rate is for each uh, lane group, and capacity is for the entire intersection. Okay, so summation of V by S means take the V by S ratio for each lane group and add them. Okay, so and capital L is the total lost time. So I'm sorry for this confusion because we used capital L as the length of the vehicle earlier, but this is what we have in the book. So you know, I didn't want it to change it because it may create confusion when you look at the book. So just keep in mind when we use L in the clearance interval equation, it means the length of the vehicle. When we use capital L in the capacity equation, it means the total lost time. Okay, so total lost time is summation of lost time for all phases. The range of cycle length which is considered as normal or reasonable is from 40 to 180 seconds. If it is between 40 and 180 seconds, then we round off the number to the nearest 5 seconds. If it is more than 80 seconds, then we round off the number, whatever cycle length we are getting from this equation, to the nearest 10 seconds. So for example, you got a number 32, 32 less than 40, so it's not considered reasonable. Let's say you got a number 42 seconds, okay, from one of these equations. So I will round it up, always round it up to 45, nearest 5. Okay, if I had got 47, I will round it up to 50. And if I got a number, for example, 82, okay, so now it's more than 80 seconds, so I will round it up to 90. Okay, if I got 96, I will round it up to 100. Okay, so this is because less than 80 is already a small number, so you don't want to make a very high increase in this small number just because of rounding up. Okay, so that's why. Then we calculate the total effective green time. So if you remember, effective green time was phase time minus lost time. This is for one phase. If you want total effective green time for the entire cycle, then total cycle length minus total lost time, which you see over here. And based upon that, you can calculate the G by C ratio as well. You already have the cycle length. When you do C minus L, you will get the total effective green time. So you can calculate G by C ratio. Okay, now you want to calculate the effective green time for each phases. Remember, you have already made the phasing plan. So this is total effective green time. V by S ratio for the lane group in the phase which you are considering right now. So I is the phase you are considering right now. So I'm calculating effective green time for phase I. So V by S ratio of that phase for the lane group in that phase upon the total V by S ratio. Okay, so this will give you, so you will repeat it for each phase and you will get the effective green time for each phase. Then I need the actual green time for running the computer logic, for running the signal. I need to show for how much time the signal should remain green. So I will use the same approach which I used for calculating effective green time. Now I already have effective green time. I already have yellow time. I already have all red time. I already have lost time. So I will now back calculate the actual green time. Okay. So effective was phase time minus lost time. So now I will reverse it. Okay. The phase time includes green, yellow, and all red. Okay. So this was it. This is the equation. Green plus lost time, both lost time. We have a startup lost time, clearance lost time. So effective green plus lost time should be equal to the phase time. Okay, so lost time I have, effective green I have, yellow and all red I calculated, so I will calculate effective green time from here. The last thing which you do is perform pedestrian clearance check. If the pedestrian is allowed to pass from that signal, you will perform this check, and the check says that the phase time should be less than equal to the pedestrian time required. The phase time, green plus yellow plus all red, should be equal or greater than the time required by the pedestrian. Now, if you go back to the coding which we were doing, you remember the pedestrian movement is given the code of the movement which is happening parallel. So 4p will happen here and 8p will happen when this 8 is happening. Okay, so this movement time, the time required by this movement should be equal or less than the phase time I'm giving for this movement 8. So the time required by 8p will be checked against the phase time of 8. The time required by 4p will be checked against the time of 4. So I'm assuming that this movement or these pedestrians should go when this movement is happening, and so on and so forth. And this is what usually happens. You see the cars going in the parallel direction, you start moving. So how do I calculate the time required by the pedestrian? So this is the equation here. Okay, so we have the pedestrian walking time. So pedestrian walking time, you can they have given us a range 5 to 7 seconds. Okay, so for one pedestrian we are saying that he will cross the road in 5 to 7 seconds, one of them. Otherwise you can calculate, okay, the average time for pedestrians who walk. Okay, and then we have the flashing don't walk time. So when the signal is becoming green or the signal is becoming red for the pedestrian, it is about to close for the pedestrian. So just like we do for the vehicles, we give them yellow time. So pedestrian, the yellow time is like the flashing. So signal is about to turn red. So we are warning the pedestrian that it is about to happen. So move fast now. If you are already on the road or you are close to the road and you want to cross, do it fast. The signal will turn green. Signal will turn green for the traffic now. Okay, so there's very short time for you. So we call it flashing don't walk time, and obviously you see the signal flashing, you walk faster. So that's why then we calculated using the speed of the pedestrian. So the width of the intersection upon the speed of the pedestrians. Remember, the width is in the direction of travel. In the direction of travel. So if you are going like this, width will be the direction. Let me show it here. So if the pedestrian is crossing in this direction, the width will be this one, this dimension. Okay, if the pedestrian is crossing in this direction, the width will be this one. So that means you have to do it for each direction. Okay, because it will not be same. The speed of the pedestrian, they are saying 3.5 feet per second can be taken, or if you do your own study, then it should be the 15th percentile speed of the observed values. Okay, so this is the procedure, and you can go through it, and we will be doing some examples, some numerical examples in which so that we can review it, how the procedure is applied actually. So this is it for now.